So, you're an engineer. You're tasked with building a brand new system, and you're staring at this massive unknown. How many people are actually going to use this thing? Is it 10,000, a million, maybe more? Designing for that kind of uncertainty is, honestly, one of the biggest challenges out there. So, where do you even start? Well, the answer is estimation. It's this incredible skill that turns what feels like a wild guess into a solid foundation for everything you build. Okay, let's get into it.
To really get a feel for this, let's start with a classic question. This is the kind of thing that pops up all the time in those tough system design interviews. How much storage space would you need for just one day of tweets? Now, at first glance, that feels impossible, right? Like, how could anyone know that off the top of their head? But it's not. It's actually a puzzle we can totally solve with the right way of thinking.
So our first tool in the toolkit is the educated guess, or what engineers love to call a back-of-the-envelope calculation. This isn't just, pulling a number out of thin air. It's a really quick, logical way to get a sense of the scale of a problem. It's fast, it's surprisingly effective, and it even has a proper name.
It's called Fermi estimation. It's named after the physicist Enrico Fermi, who is basically a legend at making these mind-blowingly accurate approximations with almost no data. The idea behind it is actually pretty simple. You take a big, scary problem, and you just chop it up into smaller, bite-sized questions that you can make a reasonable guess about.
And this right here is the absolute key. The goal is not precision. It's not about getting the answer right down to the last byte. No way. It's about being in the right ballpark. We want an order of magnitude correct answer. Are we talking about gigabytes, terabytes, or petabytes? Answering that question is the win here. The process, the reasoning, that's what really matters.
Now, this might sound a little loose, a little like magic, but it's not. There's actually a structured 5-step framework you can follow every single time. It makes this whole process way clearer, it's repeatable, and honestly, it's a lot less intimidating.
Okay, so here it is. Step 1, clarify. What are we actually solving for? In our case, it's daily storage. Step 2, divide. Break that big problem into smaller pieces. 3, assume. Use numbers you kind of know as reference points, and this is important, state them out loud. 4, calculate. Just do the simple math. And finally, maybe the most important step of all, sanity check. Does the final number even seem plausible?
All right, let's run our Twitter problem through this framework. First, assumptions. Let's say Twitter has about 250 million daily active users. Sounds reasonable. But not everyone tweets, right? So let's guess that maybe 20% of them do. That gives us 50 million users sending tweets. And if they each send about 2 tweets a day, that's 100 million tweets every single day. Now, how big is a tweet? It's not just text, there's metadata. Let's ballpark it at 300 bytes. So 100 million tweets times 300 bytes gives us 30 billion bytes.
Which is about 30 gigabytes. And just like that, we have an answer. Is it perfect? Nope, not even close. But does it give an engineer a crucial sense of scale for designing a database, for planning costs, for thinking about the whole architecture? Absolutely. We're in the right ballpark. And for that initial design phase, that's everything. Okay, but what happens when the ballpark isn't good enough? There are definitely situations, especially with things like critical network performance or service-level agreements, where an educated guess just won't fly. You need more. You need a guarantee.
And this slide just lays it out so clearly. We're really talking about 2 different worlds of estimation. Over on the left, you've got Fermi estimation. That's all about planning, high-level architecture. The output is a ballpark figure. But on the right, you have precise system measurement. This is for things like real-time analysis, where the goal isn't a guess, it's a provable performance guarantee. This is where we shift from the art of the guess to the hard science of measurement. See, to make those kinds of guarantees, we can't just rely on assumptions about how users might behave. We need something way more rigorous. We need a system-theoretic approach that can give us a mathematical promise of performance no matter what kind of chaos gets thrown at the network. And this brings us to a more academic but incredibly powerful way of thinking about things. It comes from a field called network calculus, and it basically gives us a formal language to describe and predict exactly how a network will behave under stress.
The core idea here is something called a service curve. The easiest way to think about it is like a contract or a promise. It's a graph that says, no matter what happens, I guarantee that this network link will provide at least this much service over any given amount of time. It's a floor, a minimum performance level you can absolutely count on.
So how do you calculate these promises? Well, engineers use a special kind of math called min plus algebra. I know, it sounds a little intimidating, but the idea behind it is actually pretty genius. If you look at the slide, you can see we're just swapping out standard operations. Why? Because this math is perfect for modeling how networks actually work in the real world. For example, your data flow is always limited by the slowest link, the bottleneck, right? Well, in this algebra, addition becomes minimum, which captures that bottleneck effect perfectly.
So the huge payoff here is that by using this formal method, engineers can stop guessing and start calculating. They can model exactly how a whole chain of network links is going to behave and figure out end-to-end performance guarantees with total mathematical certainty. It's a game changer.
Okay, so let's zoom out. We've seen two very different approaches, right? On one hand, the quick, directional guess, and on the other, the precise mathematical proof. Great engineering isn't about picking one over the other. It's about building a toolkit and knowing exactly which tool to pull out for the job you're facing.
And this mind map really brings it all home. Think of this as your estimation toolkit. For that early stage system design and planning, you're on that top branch. You're using back-of-the-envelope thinking to get that crucial sense of scale. But when you're dealing with mission-critical performance and you have to make promises, you're on the bottom branch. You need those precise, system-theoretic measurements to get provable results. Each one has its perfect use case.
And you know, it all boils down to this. The most important skill isn't just being able to do the math one way or the other. It's about deeply understanding the problem you have in front of you. Are you just exploring possibilities, or are you making a promise you have to keep?
So I'll leave you with this. The next time you're faced with one of these big questions of scale, just ask yourself, what problem am I really solving here? Do I need a quick guess to point me in the right direction, or do I need a mathematical guarantee that I can bet my job on? Which tool will you use?